Hello, we are going to look at a problem dealing with forces in motion and particularly on an incline. So this problem reads, you are watching a 5-kilogram mass slide down a ramp. The coefficient of kinetic friction between the block and the ramp, so mu sub k, is equal to 0.15. The ramp makes an angle of 20 degrees with the horizontal. The block starts from rest at the top, having just broke static friction, and the length along the incline is 2 meters. So the length that the block will travel is 2 meters. Find the velocity of the block at the bottom of the incline. All right, so what is the velocity of the block at the bottom of the incline? Now, we are going to examine this problem as if it's a one-dimensional motion problem. Once we do that, then we really have a constant acceleration problem because that dimension is along the incline, and therefore the acceleration is along the incline. We're sort of in a one-dimensional state. So we're interested in velocity. That's kinematics. So we're going to start with the kinematics process. So that process begins with an object, defining what that object is. Well, we're interested in what? Well, the block. So our object is the block. We also want to sort of frame our problem. What is our initial and final? When do we start carrying and when do we end carrying? Well, we start carrying as soon as the block starts to move. So right after it breaks that static friction and it starts to move down the incline. And when do we stop carrying? Well, when it reaches that end of the incline. So that's going to be at after it travels that 2 meters. Okay, with the kinematics process, we have to define an origin. So let's define the origin, perhaps where the block starts. We can choose any point, remember, but let's define it as where the block starts. And then let's make our list of knowns. Again, this is one dimension if we consider that dimension down the block. So we have our initial position, final position, initial velocity, final velocity, acceleration, and time. Now, part of identifying that origin in that picture is really recognizing the direction, okay? So our coordinate system, our positive and negative direction. Now, by convention, we use rights positive, lefts negatives, ups positives, downs negatives, but this is sort of different. It's kind of on a ramp. So we do want to identify what our positive direction is. And I'm going to look at that positive direction as being up and to the right, up the ramp, and the negative direction being down the ramp. And then that will identify for us our coordinate system that we're going to need in a little bit, and also sort of initial and final positions and directions. So our initial position is 0. That's where we've defined the origin where the block starts. Our final position is when we get to the end of the ramp. It's 2 meters away, but it's in the direction I've defined as negative, so it's minus 2 meters. Our initial velocity, well, just breaks that static friction. We're just getting to move, so it's 0 meters per second. We don't know our final velocity, but if I've defined that direction of down the ramp as negative, we can start to think about what we expect it to be. And we do expect it to be negative and non-zero. We don't know our acceleration, but again, if I've defined that direction down the ramp as negative, and I'm starting at 0, and I'm speeding up, the acceleration and the direction of motion need to be the same. And so we also would expect our acceleration to be negative, non-zero. And we don't know the time. Okay, so that's what we're interested in our list for. Right? Well, what do we want to solve about this problem? It says find the velocity at the end of the ramp. That is our final velocity. And so now what tool do we want to use? What equation do we want to use? Well, I have initial and final position. One final velocity, so that needs to be in my relationship. I don't know the acceleration, and I also don't know the time. So I only have 2 equations that have final velocity in them. One requires the time, and the other one doesn't. Well, I don't know the time, so let's start with the one that doesn't require the time. So that relationship is our relationship that says v final squared equals v initial squared plus 2 times the acceleration times my change in position. So v final squared is indeed what I want, so that stays what it is. V initial squared, well, that's 0 squared, plus 2. I don't know my acceleration. My x final is minus 2 minus x initial of 0. So let's just simplify that real quick. We have v final squared equals minus 4 times the acceleration. And so v final is going to equal plus or minus the square root of minus 4 times the acceleration. I need that acceleration in order to solve the problem. Well, I could look at kinematics to find that acceleration, and I'm not going to be able to get it. Because if I go after something else, I still need time, which is unknown. So we want to recognize, okay, what else is the acceleration related to? Well, what causes acceleration is forces. So the acceleration is related to forces, so let's do a force analysis on this block. All right, so if I were to draw a free body diagram, that's my force analysis process on that block. What are the forces that are interacting? What are the objects that are interacting with that block to cause the forces? So we'll do a free body diagram and a force tree sort of at the same time. So we know that the block is interacting with gravity. That's between the block. Remember, in our force interactions, our object we tend to put first. So the block and the earth. And we know that that is relative to the earth horizontal. The force of gravity is down. And we also know that's equal to mg. So that's just that friendly reminder to us that the force of gravity is mg. The force is also interacting with the ramp itself. So we have the normal force, that's between the block and the ramp. And it's always perpendicular to that interaction. So here's my ramp. Well, perpendicular to that ramp is going to be up and to the left, like that. Well, we're told there's friction on the ramp. So friction, the kinetic friction, as the block is sliding down the ramp, then there is our kinetic frictional force between the block and the ramp. And so if the block is sliding down, the frictional force is opposing that motion. Now it's always important to think, okay, we're all done with the forces, those are the only interactions. And if I'm dealing with friction, I have to make sure one of my interactions is also that normal force that is related to the frictional force. Remember, our friction is equal to mu times that normal force. And I have my normal force. It is the same object interacting. So that's, of course, the normal force that's related to the frictional force. Okay. So this is that point where we say, all right, well, what's the direction of that acceleration? So I know what coordinate system to examine. We don't want to put that on the picture, mind you, but our acceleration is down the ramp. So I can look at a coordinate system that aligns with that acceleration. Remember, I did a one-dimensional motion problem, so my coordinate system needs to align with that acceleration. So here's my new h prime and vertical prime. Okay, so we will identify each one of these forces, force 1, force 2, and force 3, and I will break them up into my horizontal and vertical prime directions. We're looking at that rotated axis. So force number 1, well, I have the force of gravity. So that's going to be, does it have a direction in horizontal? Indeed it does. That is the component of this force in this direction. So that's my horizontal force in the direction of that coordinate system, my force of gravity in the direction of that coordinate system. It's in the negative direction, so minus mg. And what is its angle? Remember, so if the coordinate system was straight up and down, but I've now tilted that ramp by 20 degrees, so it's this angle that is 20 degrees. So I've tilted, wait a second, I always get my tilts. This is the hardest part for me. I've mentioned that before. This. So here is my straight up and down. I've tilted the ramp by 20 degrees this way because my normal force has gone to the angle. This is the 20 degrees. And opposite that is the sine. All right, so that is my horizontal component. There's my 20 degrees. Vertically, I'm also pointing in the downward direction relative to my rotated coordinate system. And I have minus mg times the cosine of 20. So these angles, we really want to go slow. We want to look at that and go, what do I want to do here? So if this is my 20 degrees, and this is intersecting that 20 degrees, I've tilted my normal force from the straight up and down. As I've opened it, my normal force is tilted. So there's my 20 degrees. Okay, force number 2 lies along the horizontal axis in the positive direction. So it is a positive mu, and there is no vertical component. And force number 3, well, that's aligned in my vertical coordinate system in the positive direction. All right, so now we want to identify what do the sum of the forces equal in each of these directions. So horizontally, well, we know the object is accelerating in that horizontal, our new horizontal, down the ramp direction. Vertically, we have no acceleration in the vertical direction, so the sum of the forces equals 0. So, completing our force analysis, we have mu sub n, adding these together, minus mg times the sine of 20 degrees is equal to the mass times the acceleration in the horizontal direction. That's what I need. And vertically, we have the normal force minus mg times the cosine of 20 is equal to 0. This tells us that the normal force is equal to mg cosine of 20, and I can use that in my relationship over here to solve for the acceleration. So I have mu times mg cosine of 20 minus mg sine of 20 equals my mass times my acceleration. I'm dividing my mass out of the equation. I have my acceleration, mass is in every term, so it will cancel. We have mu times g times the cosine of 20 minus g times the sine of 20 equals my acceleration. And I got to grab my calculator back here. All right, so mu, we are told, is 0.15 times g of 9.8 times the cosine of 20 minus 9.8 times the sine of 20 is going to equal my acceleration. So 0.15 times 9.8 times the cosine of 20, that's 1.38 minus 9.8 times the sine of 20 gives me 3.35 equals my acceleration. My acceleration then is negative 1.97 meters per second squared. All right, so real quick check though, midterm, did I think it's going to be negative? Yeah, I did, because remember it's speeding up as it's traveling in the negative direction. I'm going to pop that into this relationship, so we have V final is equal to plus or minus the square root of minus 4 times minus 1.97. And we get V final is plus or minus, take the square root, 2.81 meters per second. So I have to ask myself, is it the plus or the minus? Well, I did my work ahead of time. So it is the minus. Okay, so we're moving in the negative direction as we've defined it given this coordinate system. So my final velocity for that block as it gets to the bottom of that ramp is negative 2.81 meters per second. All right, so quick recap of the process. We identify our system, right? We know we're after final velocity, so we started with kinematics. That's what we're interested in. Told us we were missing something, that acceleration, recognizing that means we have to look at forces in this case. Our force analysis has to be a rotated system if we're going to identify this as a one-dimension acceleration. So we rotate that system, solve for the acceleration, and we're good to go. All right, nicely done.